We've had a 45-minute break. Hope you enjoyed and made new contacts, exchanged important information. Yeah, I'll walk quickly through the rest of the agenda. So our next speaker here is Valentin Borrico. Do I pronounce your name correctly? Right. Yeah. And he's presenting his lightning talk about one model to learn them all. Gonna hear more about this. And then it's gonna be me, Alex and Jan presenting you the latest news and hot topics in deep learning. And then, yeah, we can do more drinks, beers, networking, hopefully more food. Yeah, please take a seat, everyone. And I'll hand over to Valentin Borrico.
Thank you. Thank you. So this topic would be about multimodal learning and Google's approach to create one such model. So multimodal learning is about finding or creating a model that will learn different modalities and can have such features as getting input in one modality and getting output in another modality, or making transfer learning when one modality complements another one. So for example, when you learn to translate from one language to another, you can also complement learn kind of skills or weights to translate into another language. Then we have that, can we create such a framework of deep learning to solve a multimodal learning problem? Yes, we can, and there are different approaches to this. So there are restricted or deep Boltzmann machines, there are autoencoders, there are embeddings into joint space, and other approaches that can help us to do so. And this is an example of the Google's work. They created a model that can take, for example, an image and then to show the description of this image. And take, for example, the image and show the category, and you see the rest. So like the model is doing, one model is doing all of this. So it can be called multimodal learning program. So what we have, there are some examples of multimodal learning that already were created. For example, when you use restricted Boltzmann machine or deep Boltzmann machines, you can, for example, create a captions or learn the captions, like positioning of the caption and the image in the feature space or the hidden layers, so to speak. And approach to solve this is Boltzmann machine, so deep Boltzmann machine. It basically, like a neural network, I believe some of you already know this, but it's like a neural network, but it's a probabilistic model and it has connections both ways, so to speak, when neural network has this only one way. And in this model, we learn, we just simply maximize the probability of this function, the probability of the network. And it's called Boltzmann machine because this probability is corresponded to the Boltzmann distribution. So it's one approach that was used to make correspondence between images and text. Then also there is another one, it's embedding in the common space. When we embed the images and the corresponding text, so in this case, for example, a ship and a description that a ship is sailing in the ocean. And we embed them, so kind of multiply with metrics, so to speak, or with a series of matrices. And we then have a scoring function that measures the similarity between them. And we maximize, so to speak, the positioning of the similar images and text and try to minimize the false, so to speak, the false correspondence of the false text and to the right image. So it's like embedding in the common space. Then we also have, we can use the Kullback-Leibler divergence as a metric to reduce the distance between the audio and the image frames. So in this case, it's SoundNet architecture. I can also show you a video if I'm allowed to do so via internet. What they did, they took a video stream, and they took already existing CNN. They took the features of the CNN and learned the network that way, that the Kullback-Leibler divergence, it's basically this formula. It's the distance between two probability distributions. They try to minimize this distance to create a network, so to optimize the network this way that the distance will be minimized. And when we do so, when we minimize the distance, so here, for example, it's minimal, as we see, for example. When we minimize the distance, in this case, we can achieve the following result. Can I show the video here? Via internet. If I can, then I won't show. Can I show video, like just example of the model? Yeah, with this link. So here it's still not the models that I'm describing, but I'm just showing showcases of the already created models, multimodal learning models. Here they will show that when they get the audio input, they will try to kind of find which entity will correspond the best to the given audio. So for example, yeah, one of these videos working with it. No, one of the upper ones, yes. If it is possible to see. Okay. So it's hearing the audio stream, and it's kind of saying which text is corresponding or can be corresponded to this audio stream. Here it said sky, and then stage indoor and fountain. And another one is, for example, so in this case it says it's art gallery. Okay, who knows? So those are examples of already existing multimodal learning models. And if we go to the models that was created by Google, it has a fancy name, one model to learn them all. It was trained on the following data. It's Wall Street Journal speech corpus, it's ImageNet dataset, then image captioning dataset, and then parsing dataset, and then some translations dataset. The model's architecture includes attention, series of DeFi separable special convolution blocks, encoder, decoder, and dot product attention. This model has special type of convolution. It's called DeFi separable convolution. It allows to, and also with Bayes normalization. So it allows to have a computation of a CNN to allow it to compute the convolution faster, because we don't have like 3D blocks. We have only 2D blocks, 2D filters in our convolution, and also we have Bayes normalization. And here they also use attention that is pretty typical in such kind of models, encoder decoder when we kind of learn on sequences. They use attention to choose the right parts. To choose the right parts of the sequence to apply the modality to. For example, in this case, when you would use no attention, for example, and when you would ask what is the color of the code, and when you get such an image, traditional question answering would say that it will analyze the whole image, analyze the question, and give the answer that is brown, which is wrong. And with attention-based, you find a code, so we have a kind of attention model or neural network that finds the code, and then judge the color and gives you the answer, yellow. So this is a scheme of attention model. It's where we get inputs with LSTM, like memory, long short-term memory units. When we get inputs, and then we put it through attention, that choosing, so to speak, the right parts of the sequence to compute. And then we also use decoder. And then we put back again decoder and decoded output and next input to generate a sequence. So like we make sequence-to-sequence learning. They also use mixture of experts layer. Mixture of expert layer is using gating function, again some neural network, that is learning which weight, when we have, for example, different modalities or different experts that can learn our data, that can encode our data. The gating network is using the right experts for the right data, so to speak. And it's choosing the weights to weight the output of the experts. So it's basically like back of networks or back of experts. And so they have, for each modality, they have modality blocks. And modality blocks, it's basically a convolutional step that is basic convolution. And then max pooling. So you know what is max pooling, what is convolution. And then they use the same kind of principle, so a series of convolutions for different modalities. They created the similar model to the joint image text space, so to speak. They encoding the input with spatial tricks, and then they decoding and generating a right sequence. So with all of this said, they show that their result on the top result of their model that is trained simultaneously on 8 different tasks or corpuses that were presented before is achieving 86% accuracy. Like, it's not as good as the state-of-the-art model, but still, like, they are trained simultaneously on different modalities. And also the Bleu score is it's the score of how good the translation model is. They're showing that it also like worse than state-of-the-art models, but still they do it simultaneously on different modalities. And I find it pretty interesting. And just to sum it up, the multimodal learning can be solved with different approaches. So this model is not the new one, but is more general one. So it considers more modalities and has more tricks that saves computational time and do, for example, batch normalization and attention and so on. And yeah, so I stated here. And the outlook would be is to learn or to look up more on the transfer learning as well as one-shot learning when you don't need a lot of examples, you need only one example to learn the representations. And memory networks, so there are also memory networks with memory states, and one can also use attention to find a right memory state or memory units to use to train the model. So basically it was it. Yeah. If you have any questions. Okay.
Yeah, let's open the floor for questions. Are there any questions about this part of our meetup, of Valentin's talk? Yes, please. Jan. Here we got our audience microphone.
Hello, thank you for your speech. I have such question. Can this approach be used, for example, for combination of processing and generation? For example, text processing and generation of some brief description?
Again, your question, when we...
Can we use so with the multimodeling?
Yeah, I mean, basically, when we have sequence-to-sequence learning, we can use this model. So like when we read one text in... give me an example. So like one example would be to translate from one language into another language. So it can be used in this way. And also if you have one sequence and it should be corresponded to another type of sequence, it can learn it. Yeah. Okay. It can learn the right, so to speak, weight or representations.
Are there more questions? Yes.
Is there a way to enforce that each of those experts is somewhat different, or does the network learn it on its own?
Are the experts different, or?
Yeah, is there a way to actually, if I would train, for example, random forest, and each tree would be the same, then there's no point in training a forest. If I train this network where I kind of gate each of the experts, can I somehow enforce that each of the experts is learning something different and complementary to the others?
Yes, by using gating networks, you correspond the given input to the given expert, and it's learning the corresponding modality or the corresponding kind of functions that it has. And again, those are neural networks and not random forests in this case. So different types of neural networks with different convolution layers.
Nice. Another question from the audience. Alex, are you checking the YouTube channel? No questions there? Okay. Do you have a question? Yeah, then let's conclude. I mean, you're still here, right? After the next block. If there are more questions,
yes.
just you're open for discussions.
Yeah, sure.
Yeah, and we're gonna provide the slides to the people.
Yeah, sure. No
Okay,
problem.
good. Then let's thank Valentin again.
Thank you for the attention.
Thank you.